Yeah, thanks so much for having me. I've had a great time here so far. So today I am going to talk about tidal disruption events, which we generally abbreviate to TDEs, but I will try not to use too many stronger abbreviations today. And so these events occur when a star gets too close to a black hole and is ripped apart by the tidal gravity and eaten. And this is obviously intrinsically cool, or at least I think it's obviously intrinsically cool, but it also can tell us a lot about the black holes that are disrupting the stars and also about the populations of stars surrounding them. And so just for motivation, I write down a couple of big questions that we hope that TDEs can help us answer in astronomy. Oh, sorry. Oops. Opposite. Is that good? Yeah, better? Yep. Great, cool. Sorry about that. So one of the big questions that about supermassive black holes is actually maybe the simplest one you could think to ask, which is just how did supermassive black holes get so big? And a related question that can really help us answer this is, what is the mass function of black holes? And so hopefully by the end of the talk, you'll see how tidal disruption events can start to help us answer these questions. And so to begin with, when we talk about black holes in astronomy, we often talk about two main different size scales. One is stellar mass black holes. And these are approximately similar to the masses of the stars that form them normally by exploding in supernovas. So 1 to 100 solar masses or so, twiddle. I'm going to be dropping factors of 2 throughout. And then there are the supermassive black holes at the centers of galaxies. And these guys the lower mass end, maybe you could go a little bit lower, but let's say of order millions to tens of billions of solar masses, so just completely disparate size scales. And so if you wanted to grow a stellar mass black hole to the size of a supermassive black hole over the age of the universe, you would need to be growing the largest ones at about 1 solar mass per year on average. Now, obviously, you could do that at different times, but it turns out that this rate is above the theoretical mass accretion limit for black holes that are below about 10 to the 8 solar masses or so. So for most of this growth period, if they were, I mean, they could grow more later, but they'd be growing at this really, really close to this accretion limit. Now, this is a very simple picture. In reality, we think that the seeds black holes that will eventually grow to be these supermassive black holes might start at larger masses. You could have early, what we call POP3, confusingly the early stars called POP3, that are slightly more massive, and that helps a bit. You can even help yourself even more if you allow for direct collapse of large gas clouds, and then you can start at maybe 100,000 or so solar masses. But regardless, there's still this tension between the very, very largest black holes that we see and how they form at lower masses because of this accretion limit that I'm talking about here. And so what is this accretion limit? This is the Eddington limit, and it's just the point where the radiation force is approximately equal to the gravitational force. And so these accreting black holes are so bright, they're so efficient, because essentially what you're doing is converting the kinetic energy of the orbiting gas into observed luminosity. And gas that's orbiting these black holes is orbiting at an appreciable fraction of the speed of light. And so if we were to write down a luminosity for one of these events, or sorry, for accretion onto these black holes, we normally just write it as m dot c squared times some efficiency, where the luminosity is just power in astronomy in units. The efficiency is often of order 10%. And so even if you think about the nuclear reactions that are happening at the centers of the sun, you're only going to get efficiencies of order like 0.7% for turning helium or hydrogen into helium. So this is really high. And so these accreting black holes should be very bright. And because of that, you can get to the point where they're so bright that they're pushing back against the infalling gas. We can calculate where this happens. I generally like to do this by thinking of the radiation pressure, so times some cross section. So I can write down, this is a power, so energy per time, divided by some surface area. We're going to do this in spherical symmetry, and we'll talk about how that breaks down later. So this is energy flux divided by the speed of the photons times some cross section, balancing the orbital, the gravitational force of the infalling debris. And so if you rearrange this, you get, this is the pressure I was talking about. That's the cross section. You get this really simple term that is not dependent on the size of the object. So this is totally dependent on the mass. And I've pulled in the cross-section over the mass in the denominator here because this is just an opacity. And so it depends on the properties of the infalling gas. We often assume that the majority of the gas is ionized hydrogen, which is simple, but also ends up being pretty accurate in many of these cases. And so we can use a Thomson's opacity for electron scattering. And then you can plug in numbers here. And if we first just do our sun, because then we can maybe have a bit more physical intuition, the Eddington luminosity for an object of mass our sun in astronomy units, in CGS, it's 10 to the 38 ergs per second, but this ends up being about 4 times 10 to the 4 solar luminosities, so over 10,000 times as luminous as our sun is right now. And if you then think about the black holes that are much more massive, if we take the black hole mass of Sagittarius A star in the center of our own galaxy, that's 4 times 10 to the 6. We get something that's about 10 to the 11 solar luminosity. So just incredibly bright. So if there are black holes accreting at these luminosities, we would expect to be able to observe them. But it turns out that in our local universe, at least, the majority of black holes are not actively accreting in what we term as, we often call them active galactic nuclei, or AGN, but are in fact quiescent. And so we cannot observe them directly from the luminosity of the mass they're pulling in. And so if we want to think of the black hole mass function, most of my axes will be in log, but occasionally I will let you know if that changes. And the black hole mass function, again, is closely tied to how quickly black holes can accrete. Put a few numbers on these axes. 10 to the 5, 10 to 9. And we're starting up here at -2, down here at -6. Cool. The accreting black holes, the relative number of accreting black holes is way down here. This is 10 to the 6, 7, 8, 6. There we go. Looks something like this. And the relative number of quiescent black holes is something like this. And so it is orders of magnitude higher. It does drop off at the higher mass end, but there's actually a lot of uncertainty at this lower mass end where we think there should be way more black holes. And the reason for this is just if we're not studying them because they're actively accreting, then generally the way that we're studying them is by looking at the dynamics of gas and stars that are in really close orbits. And this is a lot easier to do if you have more massive black holes, simply because the radius at which the velocities are really high is going to be larger. And so I would say this section is pretty well measured, even if the black holes aren't accreting at super high rates. But the region below 10 to the 7 solar masses or so is a lot more uncertain. And so one of the ways that TDEs can help us out is, one, they will bring galaxy or black holes that were previously quiescent, they didn't previously have this mass supply, and they will bring them gas and they will light them up and they can bring them to close to the Eddington limit. But also they are preferentially probing lower mass galaxies. And so TDEs, most of the TDEs that we observe are actually coming from black holes that are below 10 to the 7 solar masses or so, because once you get to large enough black holes, the star is actually disrupted inside the event horizon, so you can't. So we're forced to be preferentially observing the lower mass ones. But that's actually great for better understanding the population at that mass range. Okay, so hopefully that's a bit of motivation for why we as astronomers care about them beyond just liking to look at stars getting ripped apart by black holes. And so in the next part of the talk, I'm actually going to start thinking a little bit more about the physics that's going into the disruption process. And the first thing is I just said that stars will only get tidally disrupted below, it's actually around 10 to the 8 solar masses or so. And so to figure out why that is, we want to calculate the tidal radius of disruption. And so this is a great place to think about tides. The ocean is right outside. But a quick refresher here, if we have some, actually this is a little bit unfairly large. It turns out that the size, the actual event horizon of a black hole that's around in like the center of our own galaxy is not that different from the radius of our sun. So I should draw these as more comparable. And then the tidal radius, the tidal force is just the difference in the forces on the two sides of the star. You can do this in your dynamics class to calculate tides on Earth, right? And so what we end up finding is if we just really quickly. subtract these two, we can pull out a bunch of terms and then Taylor expand the bottom, and we get a pretty simple equation that is just the original force of gravity on the center mass of the star from the black hole. Oops. Times the ratio of the star's size to that distance. And so that's the same tidal gravity that you have in any sort of system. But it's important for us to have it here, because when we want to define where a star is fully tidally disrupted, what we want to do is set this tidal force equal to the self-binding force of the star. And so if we want to calculate the tidal radius, what we're going to do is set Ft here equal to F bind, or F self-gravity, however you want to term it. I'm not going to do the integral, but this just goes as gm star over r star with another factor of m star, because it's the self-gravity of the star. And so you can do this and solve for the radius where they're equal, which we define as the tidal radius. And we get this really, really nice simple equation that's just dependent on the properties of the star and the black hole. And this is also a very similar equation used in, for example, binary dynamics to determine when one star will start to strip the other star of its outer material. And so all it's dependent on is the radius of the star, the mass of the star, and the black hole mass. It does vary a bit with stellar structure, but it doesn't vary more than a factor of a few generally. So if you have a more compact star, if you have a more compact star, it's going to be disrupted at smaller radii, is basically what this says. If you have a puffier star, you're going to be able to start stripping it at larger radii. And so then what we can do, once we have this, is calculate when we can compare it to the actual size of the black hole doing the disruption. And so black hole's radius, Rg, is just g mh over c squared. Again, factor of 2 there. This is technically for a maximally spinning black hole, but I'm ignoring factors of 2. And so you can you can calculate what this is and compare it to the tidal radius. I said before that this tends to be equal around 10 to the 8 solar masses. It does depend on the spin of the black hole and the properties of the star. But I'm just going to plug in numbers here. For our own galaxy, we have Rg is about 5 times 10 to the 11 centimeters, which is mentioned earlier, I think about 10 solar radii, so not actually that different in size. And then if we go over here and plugged in numbers, what we would find is that the tidal radius, again for our own galaxy, and I'm using a mass of a sun like a star like our own sun, you get a value of about 10 to the 13 centimeters. And so our own black hole could disrupt our own sun, but if it got about 100 times larger, it would become difficult. And so one of the actually really cool things on the observational side that we're already seeing is that when we look at the black holes that are disrupting the stars that we're observing in our tidal disruption events, we are starting to see this event horizon suppression, which is also really good for convincing us that what we're seeing is actually the disruption of stars. And so if you didn't have any of this event horizon suppression, you'd expect the rate to decrease a little bit with black hole mass just because of the properties of the density profiles of the stars and the cusp. But with this event horizon suppression, you get a really steep drop off between 10 to the 8 and 10 to the 9, depending on how fast your black hole is spinning. If it's not spinning at all, it's around 10 to the 8. It starts to get closer to 10 to the 9 if it's maximally spinning. And we actually are seeing this in observations of TDEs, and so we're already being able to use that to help look at the black hole mass function at smaller masses. Okay, so these are two relevant size scales for disrupting stars, but where do these stars actually come from? Black holes are really big compared to stars, but they're actually not very important dynamically on the scale of the galaxy, right? So our galaxy mass about 10 to the 12 solar masses. Our black hole mass, well, ours is about 4 times this, but it's about 1 million solar masses. And so the majority of stars in the galaxy are just kind of orbiting other stars and dark matter. They don't actually know about the black hole at the very center. And so to get to the part of the galaxy where the black hole actually influences dynamics, we call this the sphere of influence. This is actually a pretty good name. And this is where the mass enclosed is approximately equal to the mass of the black hole. And so these stars do know about the black hole, and it is influencing their dynamics. But the sphere of influence in our own galaxy is about a parsec, which is about 10 to the 18 centimeters, which, oh damn, I erased the tidal radius, which is about 10 to the 5 times the tidal radius. And so if one of these stars is going to be disrupted, it has to be on a very eccentric orbit. And it's also mostly going to be coming from the outer regions, because that's just where most of the stars are. And so if you write down a density profile, we normally, sorry about the 2 alphas, we normally use alpha to define density profile. We also generally are using just power law density profiles to describe these cusps. But reasonable density profile values, the exponents, is like 1 to 2 or so. And so even though this is pretty steep, these are cuspy centers of the galaxies. They have nuclear star clusters. They're very dense. The majority of stars is still living very, very far from the black hole. In fact, 10 to the 5 orders of magnitude or so away from where it would get disrupted. And so we can think a little bit more about the orbital dynamics that will actually lead to disruption for one of these stars. So if we have a star on an orbit around the black hole, it has to be very, very eccentric on this nearly radial orbit to actually be able to hit the black hole. We have the pericenter radius, which is just the semi-major axis times 1 minus the eccentricity. We have apocenter, which is 1 plus the eccentricity times the semi-major axis. The pericenter radius, again, to be disrupted, 10 to the 13 centimeters. This is 10 to the 18 centimeters. And so you can, just in your head, calculate that the eccentricity is basically approaching 1. It's like 0.9999 for many of these disrupted events. And that's interesting for calculating the angular momentum of the orbits that will actually produce these disruptions. And so angular momentum is just a formula for angular momentum. It's just gm a times 1 minus e squared. We can write this in terms of the pericenter radius times 1 plus e. But like I said, e is basically 1. And so this gives us a really cute little formula for the angular momentum of stars that are disrupted. And so the angular momentum for a star to be disrupted has to be less than this. And we call this the loss cone of orbits that will be disrupted, is stars that have angular momentum less than this value on these very, very radial orbits. And so why do we call it a loss cone? Erase this. You guys know it's TDEs by now. If the star is moving in this direction, this is its velocity vector. I wrote down I'm really doing absolute values of angular momentum, but if you actually think about it as a vector, then at a given radius, the direction of its velocity is going to determine the magnitude of the angular momentum. And so if this is the tidal radius of this black hole, this star is definitely going to be disrupted. In principle, the star could be on a slightly different orbit. And still get disrupted by that black hole. And so this is what we call the loss cone of orbits that will be disrupted, such that the angular momentum is within this absolute value for disruption. But you can also think of it directionally, and I think that makes a little bit more sense for why we call it a loss cone. But what is the process that actually moves stars onto these disrupting orbits? So if they were just purely, if it was just a single star orbiting a black hole, it would either be disrupted or it wouldn't, and its orbit wouldn't really be changing much. You could just, or even if you had a population of stars, you could do a sort of n sigma v argument where you calculate the density, you calculate the cross section of the tidal radius, and you calculate the velocity dispersion. But in fact, the orbits of these stars are going to change with time as they interact with each other. And so we call this process two-body relaxation. So this is just a diffusive process, right? So these random kicks. Oh, I was using little l before. I'm sorry if I go back between little l and big L for this. Hopefully context will determine if it's luminosity or angular momentum. So the magnitude of the sum of these angular momentum kicks is just going to be proportional to the square root of n because it's a random walk process. And so we just, over time, these stars will encounter other stars. Some of them will manage to build up or change their angular momentum such that they will fall within the loss cone. And we kind of think about this in two different regimes. One of these is where the delta L per orbit is greater than L loss cone. And in this case, you can have a star that is in the loss cone for part of its orbit, but then it moves out of the loss cone and isn't disrupted. You could also have delta L orbit less than L loss cone. And in this case, if a star diffuses into the loss cone, it's almost certainly going to be disrupted in a single orbit. And so this is generally an empty loss cone regime, which means as soon as a star gets into the loss cone, it's immediately disrupted. Whereas this, we often call the pinhole regime because stars are like a pinball machine, are running across the loss cone in a single orbit, and they may or may not actually get disrupted while they're still in that loss cone. And it is, in this case, the loss cone is generally full because there are always lots of stars in the loss cone. They just may or may not be disrupted in a single orbit. And to think about how this actually maps to the real space where these stars are interacting, we have delta L, again, is going to be m times delta v cross r. And so right away you can see that if you have a longer lever arm, you're going to have a lot larger changes in angular momentum, and you're going to probably be more in this pinhole regime, right, where you have large changes in angular momentum per orbit. There's also the fact that if you are near apocenter in your orbit at larger radii, you can get larger changes in delta V through a sort of impact approximation because you're feeling the gravitational influence of other stars for longer. And so in general, this regime here, where you're in this pinhole regime and you always have stars in the loss cone, is going to be the case at larger orbits, and this diffusive regime is at smaller orbits. Yeah? Sorry, yeah, this is the number of interactions. So it's this is the square root of n is like a random walk process. So your root mean square adds up. But these are number of interactions. And so it'll be higher if your number density of stars is higher.
So there's a mean free path that you know?
Yeah, and so I'm not going to go into the detailed rates calculation because you generally need to solve a Fokker-Planck equation, and I don't want to do that on the board here, or try to. But yeah, so you're doing really detailed calculations to determine the both the number of interactions and the relative effect of each of those interactions. And so the big takeaway is unless your density profile is very, very steep, if it's just kind of going between 1 and 2, if you have more stars, you're going to diffuse faster, you're going to have more interactions, you're going to have, and if you have less stars, it'll take longer. But an interesting thing to note here is actually the regime where we, oh, yep, sorry, one more.
So this is in a given system?
This is a given system, yeah.
Are the data good enough to...
Oh, no, keep going. I think I know where you're going. I hope I know where you're going.
Are the data good enough to perhaps consider averaging over the multiple systems that are sort of similar and somehow the statistics?
Yeah. Yeah, so actually so to calculate these rates more precisely, what people have done is actually look at real systems and try to put in the parameters for like different cusp steepness at different black hole masses to try to more accurately calculate these rates. It is difficult because it's actually very, very difficult to resolve down to the sphere of influence. So for most of these, we'll talk about later what these actually look like. Most of the times when we're actually observing these, we can't resolve the stars even at the sphere of influence.
I was going a different way, which is that once you imagine just for fun, maybe if one could correct for variations between different systems, maybe there's some sort of universality in how these collision processes are taking place. You can imagine that you could essentially assume, even though it probably isn't realistic for a given system, assume that you're dominated by some sort of universal effects coming from these collisions that push things into the loss cone. And so it would still be somewhat predictive if you aggregate over many sort of observations.
Yeah, I think I understand where you're, if I understand, so I think people do something kind of similar where they are, when they do calculate rates, they try to do something like that where they're kind of, I guess, yeah, they're looking at a bunch of different systems that are different and they aren't individually predictive of all rates. And then they are doing an averaging. Oftentimes it'll be as a function of mass just because that's useful. So yeah, the plot that I showed, or the thing that I had earlier was the approximate rate of TDEs as a function of black hole mass. It kind of slopes down a little bit at increasing mass, and that is actually from looking at the properties of galaxies as a function of mass. Yeah, no, that's really interesting. Okay, yes. So it turns out that where we get most of the TDEs is actually where delta L orbit is approximately the size of the absolute value of the lost cone angular momentum. And purely by coincidence, this actually is pretty close to the sphere of influence radius for the black holes that produce most of TDEs. So if TDEs were coming from larger mass black holes, this would no longer actually be the case. The radius where most of the, we'll call it the critical radius where most of the stars are coming from would be at larger radii. But as it turns out, it's very easy to remember for us in the TDE field because most of the stars are coming from near the sphere of influence. So the sort of approximations we were talking about earlier in size scales are pretty relevant for the majority of these events. And then kind of going on what your question was earlier, if you do an aggregate rate based on these sorts of calculations, you get a rate of about 10 to the minus 4 per galaxy per year. And so it is certainly lower than the supernova rate, but if you look specifically at the nuclei of galaxies, which is what the observers who are trying to find these do, we have been able to find a substantial number, especially over the past 5 years or so. So after a star is within the tidal radius of the black hole, what happens next? So if we have our orbit, if the eccentricity is approximately 1, this means that the orbital energy, now there's too many E's, is approximately 0. And so this orbit is nearly parabolic. The center of the star, the center of mass of the star, is almost unbound from the black hole on this orbit. And so if you have a star coming in, and that'll become important when we try to actually calculate, do some back of the envelope math to estimate some properties here. You get these nice tidal tails that will eventually elongate and form streams of mass returning to the black hole. And in this case, where the orbital energy is about 0, half of the stellar mass is going to be bound, and half is unbound. And if we have time at the end, if you have a case where you don't fully disrupt the star, you might only pull off the outer layers that can still produce a flare. But for now, we're going to think about the case where the star is fully disrupted. The most common case that we think, which is the orbital energy is close to 0, and half of the mass will eventually return to the black hole and power the flare that we observe. And so if we zoom in on the star here, if the black hole is in this direction, the half that is going to be bound is the half that's is closer to the black hole. So all of this is unbound. But if you want to think about when different material from the star returns as a function of time, you want to think about the spread in orbital energy in the star at the time of disruption. And so this material here, that's very close to the black hole will actually return first. And it will be at very, very late times that we finally get material that's coming from closer to the core of the star. And in fact, you can imagine in theoretically, if this is a perfectly unbound star, the rate of return will approach infinity as you get close to that surface where the orbital energy was 0. Okay. And so what this allows us to do, if we think about the spread in orbital energy throughout the star at disruption, and the spread in orbital energy of the bound debris afterwards, is it allows us to define a mass fallback rate to the black hole after disruption. And this is really important because it's going to tell us how quickly mass is fed to the black hole. And there's a lot of uncertainties that we'll get to later about how that's actually converted to luminosity. But this is what's powering ultimately the flare that we see, is this mass returning to the black hole. And so we often like to break it up into 2 different components, and one is the mass energy distribution in the star, so the fraction of mass at different orbital energies, and the other is the relationship between orbital energy and orbital timescale. The reason we like to do this is because this is really dependent on the stellar structure. And also on the hydrodynamics of the actual disruption process, whereas this can be estimated analytically. And so we will go ahead and do that to get some scalings, and then go back, and there are still some analytic scalings you can get from the mass energy distribution, but to get the full behavior, what we've generally done is run hydro simulations. And another way to think about this is if you actually look at the orbits of debris that are bound to the black hole after disruption, so the half that's bound, they're still on very eccentric orbits, but the, draw one in here. But some of them are more bound than others, and it's this spread here, delta E, that becomes a delta T and gives you a mass fallback rate as a function of time. And by calculating this spread in orbital energy, we can learn about the time scales and the evolution of the mass that's returning to the black hole and ultimately powering the flare that we observe. So the first thing that we can do that was done very early on by Martin Rees in one of the earliest papers, although there's actually a typo in the original derivation, is to calculate how this orbital energy depends on the orbital time scale, so that dE dt. And so writing down the orbital energy, you immediately see that it's proportional to black hole mass over A. If you write down your equation for orbital period, you can also write down its proportionality with the semi-major axis and the black hole mass. Everything else is constants. So you can then write one in terms of the other to actually calculate dE dt. And you very quickly see that dE dt is just proportional to t to the minus 5/3. And in fact, what this also means is if the mass energy distribution is relatively constant, the entire fallback rate is proportional to t minus 5/3. And as you get closer to the core of the star, this mass energy distribution does become more constant. And so this led to the prediction that at late times we would expect the fallback rate and potentially the light curve of this transient, if it follows the fallback rate, to follow this t to the minus 5/3 power law decline. So another useful thing when trying to predict what a transient looks like is to think, this is a power law, it doesn't have any scaling in front of it right now the way I've written it, but is to think about the actual time scale of this event. And to do this, I think it's useful to think about the energy of the most bound debris that I was talking about there. That's the material on the very surface of the star. And if we want to calculate this, it's useful to remember that the center of the star is basically unbound. It's on a zero energy orbit. So you can just calculate the difference in binding energy to the black hole or in orbital energy around the black hole between the material and the edge of the star and the center of the star. And this leads to a very similar calculation for as the one that we did for tidal, the tidal force and the tidal gravity. And in fact, it is just the binding energy to the black hole times the stellar radius over the tidal radius. But then we can actually plug in the value for the tidal radius here, and we can get a proportionality with the properties of the black hole and the star. Okay, so we have energy, it's proportional to this. But then we can look over here, and we have a function for the orbital energy, or the time scale in terms of the orbital energy in terms of the time scale. And so we can flip this around and actually plug in for the time scale for the most bound mass to return here. And so we find this really simple scaling between the time scale of the mass returning, the black hole mass, and the mass of the star and the radius of the star. And so if you can't see very well here, the mass of the black hole, the time scale is dependent on the mass of the black hole to the 1/2 power, the mass of the star to the -1 power, and the radius of the star to the 3/2 power. And so if you look at this at first, it seems like it's mostly dependent on the properties of the star and not the black hole mass. But for main sequence stars, the radius of the star is actually proportional to the mass to about the 0.7, which is very close to 2/3, and so it nearly cancels out for most of the stars that are disrupted. And we end up finding that this time scale is mostly dependent on the black hole mass. And so we can use this information, this t to the minus 5/3 scaling, and we can plug in numbers to get the actual time scale for these events. And we can calculate what we expect the mass return rate to the black hole to look like after disruption. This is in log-log space, so the power law just looks like a straight line. This initial rise is dependent on the properties of the outer layers of the star, where the mass energy distribution is not so constant. It's changing more quickly. But the time scales that we end up getting for the peak is like weeks to months, where the weeks time scales are for black holes that are around 10 to the 5 solar masses or so, and the months is for 10 to the 7 greater than-ish. And we can also calculate, I didn't write it down here, but we can calculate the relationship between the fallback, the magnitude of the fallback rate and these parameters. You find it has the opposite dependent on black hole mass, which is good because otherwise it wouldn't be mass conservative. It also has the opposite dependence on the radius of the star for the same reason. But it increases as the power of 2 with the mass of the star, because adding a more massive star does increase your mass fallback rate at peak. And if you plug in numbers here, you get about 0.1 to 10 solar masses per year, depending on the mass of the black hole in the star. And so this is definitely, from our very, very early calculations, super Eddington for many of these black hole masses. So the prediction is if the black hole is actually fed at this rate that the mass initially falls back at, you would expect pretty Eddington-limited events, timescales of weeks to months, which ends up being similar to supernova but a bit longer, and a t to the minus 5/3 decline at late times. But this is all just talking about the mass returning to the black hole and not actually about how that mass is converted into the photons that our telescopes observe. And that next step is a lot messier, and we spent a lot of time at this workshop debating it, and so I will try to give an overview of it, but I'm sure I won't be able to do every part of it justice. So how is the mass converted to energy? Now, again, in the simplest terms, it is just coming from the kinetic energy of the infalling debris. It's just how that energy is released that is in question. So after disruption, the star comes in on a very eccentric orbit. After disruption, the streams are still quite eccentric. They're bound but quite eccentric, and so it's not immediately clear how this would produce a bright event, because these would need to be interacting to actually lose energy. It's certainly not in a disk-like configuration to begin with. But what we find is if this is a Newtonian dynamics picture, if you do include GR, in a lot of cases you're close to the gravitational radius. You might be of order 10 gravitational radii away. You actually do get apsidal precession. And so this can produce stream collisions, which can actually dissipate some of your initial orbital energy, allowing the gas to fall in closer and potentially actually form a disk that we would observe. You can also get shocks at the nozzle. These are a little bit less obvious. It's basically the streams are on adjacent ballistic orbits, and then they intersect at pericenter. And this looks like a vertical collapse that can also shock the gas. But because it's in the perpendicular direction to the majority of the velocity, you have access to a lot less kinetic energy, and so you're not going to be able to dissipate quite as much here as you could in a shock here. But either way, this is how we theoretically think that you can start to lose energy. And both of these processes would also produce observable luminosity. It's just that if you're colliding at larger radii, you necessarily have less kinetic energy than if you're colliding at smaller radii, and so your efficiency is less. And so the efficiency goes as v squared, and so it goes as 1 over r, the maximum efficiency does. And so you're just going to be much more efficient at smaller radii in a disk. But all of these processes can certainly release energy. If we do form a disk, we can estimate the size of this disk by conservation of angular momentum. And so our disk here is just about 2 times the pericenter radius. It's exactly 2 times the pericenter radius if you perfectly conserve angular momentum but lose energy. And so early on, before we had seen a lot of these events, we thought, well, if this process of colliding debris streams and circularizing debris into a disk is relatively quick, or rather, if the time scale for material to fall back is long compared to it, then we would expect the light curves to approximately follow the longest time scale and look somewhat like the mass fallback rates, but in luminosity, not in mass fallback rate. Yeah, so if the circularization time scale and the accretion time scale of gas moving through the disk were shorter, we were thinking, well, maybe this is an okay picture, and still the majority of the luminosity would be produced by this disk, whose size scale is comparable to the tidal radius. And so what sort of expectations did that give us? Well, the mass fallback rate is very, very high, so L would be close to the Eddington luminosity. We'd have a t to the minus 5/3 decline at late times, which is different from supernova. So if you have a radioactive supernova, then you have an exponential decay, so it's slower at early times, drops off really fast at later times. You have T peak on time scales of weeks to months. We also expected this to be coming from a disk, and so bright in X-rays. And there were a couple early candidate events that actually did match most of this, but then the majority of the events that we've seen since have they do seem to follow power law declines that can be well matched by t to the minus 5/3 at early times. They do appear to have peak time scales on orders of weeks to months. We can debate this one a little bit. They seem to be a little bit under bright, but still pretty close to the Eddington luminosities. But one of the big questions is that many of them are not bright in X-rays. They're mostly optical and UV transients. So it seems like we're not actually looking at the accretion disk that we thought would be forming, and that we generally think of for accreting black holes at all other size scales, so stellar mass black holes or like AGN. Or we weren't. And so why is this confusing? So if we just do a really quick black body approximation, if we have a luminosity of about 10 to the 44 ergs, which I said really early on is basically the Eddington luminosity for a black hole like the one in our own galaxy. If our disk radius is about the size of the tidal radius, about 10 to the 13 centimeters, and if we do a black body approximation, which isn't perfect for a disk because it's assuming it's a sphere, but it's illuminating nonetheless, then we'd expect the temperature to be greater than 10 to the 5 Kelvin or so. Even hotter if we modeled it properly, because then we'd be looking at the inner annuli of the disk as well as the outer radius. But when we actually looked at these events, there may be a few times 10 to the 4. This is maybe the median. There's a range of them. They're about an order of magnitude cooler, or even more so if you properly model the disk. And this implied, and they were actually better matched by a black body spectrum than by a disk-like spectrum. And so this is a much, much larger emitting area that you get. Just as a reminder, I'm just doing a black body approximation here where L goes as r squared t to the 4th. So if you have the same luminosity but cooler temperature, you have a much larger emitting area. This is a much, much larger emitting area than what we expected. And And a lot of this conference has been debating where this optical and UV emission is coming from. I would say that in the broadest terms, most people generally think that what this means is there's a lot of gas surrounding whatever is emitting the initial radiation. Because we seem to be seeing this black body on scales of 10 to the 14, 10 to the 15 centimeters, which implies that there's thermalization at that radii. And so if you draw, and so there's a couple things that could be putting gas at these very large radii. One is these initial stream collisions, in addition to releasing energy, also produce really large outflows in a lot of the simulations of these events that we see. Another thing is if you actually look at what an accretion disk, or if you actually model what an accretion disk would look like when it's accreting near the Eddington limit, it's not a thin disk at all. It's actually very, very puffy. For the same reason that you calculate an Eddington limit at all, the radiation pressure is getting high enough that it's actually puffing up the gas in the disk. And so it's much more, it's quasi-spherical as opposed to disk-like. In addition to this, it will launch winds and outflows concentrated around its poles, but that can also look quasi-spherical. And so all of this, if at early times you have the circularizing gas producing large outflows, and then as soon as you do form a disk that's also producing more winds and outflows, you can imagine that it's not too crazy to think about this much, much larger radius of optically thick gas inside which all of this mess of things is happening. And so we have strings colliding. Unfortunately, what this means for us is regardless of what's actually emitting the initial radiation, all we're seeing in the optical and UV is the reprocessed emission at much larger radii. And so it's much more difficult to actually get a handle on, for example, if we're actually forming a disk at early times and feeding it at super Eddington mass accretion rates, what that looks like. And so one of the things that we can do, I said the majority of these events are, most of the data that we have is at optical and UV wavelengths, but we do have a subset that shows some X-rays or some radio. And so if the source of the optical and UV is hidden, in some cases, if we do see X-rays, we can try to explain that as evidence for a disk. And we also sometimes see radio, and in more and more cases, we're seeing evidence for outflows at later times as well. And so radio is a really good probe of fast outflows, or in the most extreme cases, jets. And so one of the things that we can do is for the maybe 10% of events that have X-rays, 10% that have radio, use those in combination with the optical and UV data to try to get a better handle on what's happening during this during the peak of the emission at optical and UV wavelengths. And so there's been a lot of discussion in the workshop this past few weeks on how we can do that and improve upon that for more of our events. But I'm actually going to, I guess I'll actually draw what one of these light curves kind of looks like. And one intriguing thing is that while at early times we have this flare that in the bolometric luminosity, so in the total integrated luminosity, seems to look somewhat like the mass fallback rate at early times. For many of these events, we are seeing this late time plateau. And so this seems to imply that at very late times, the dominant time scale is no longer knows about the fallback rate. It's now something else. And that has been modeled recently as potentially being due to a viscously spreading disk. And so in this case, eventually T accretion grows longer than T fallback. And what we're hoping is that we can then model this late time disk evolution and learn more about the earlier times as well. And so when I say viscously spreading disk, if you start at early times, you have something puffy. Once you're no longer super Eddington, that can kind of cool down into a thinner disk configuration. And then as that disk continues to accrete, I don't know if I showed that very well, but it will become less and less dense, but it will spread out to larger radii, again, just because of angular momentum conservation. So your material with larger angular momentum is going to larger radii, and that's allowing some of the material to actually move in and be accreted. And so there's been some really nice work that has shown at late times, this predicts that the UV luminosity of these events is proportional to the black hole mass to the 2/3 power, which has actually been observed for many of these events. So now we find that the early time scale does seem to be mostly, does seem to know about the fallback rate. The time scale at early times for these observations is, in fact, seeming to mostly follow the black hole mass to the 1/2 power. And then at late times, we have the second relation with the black hole mass, where the luminosity in the UV is following the black hole mass to the 2/3. And both of these we sort of understand theoretically, even if there's a lot of uncertainty in the details. And so I guess kind of stepping back to the big picture here, how much time do we have? Oh, so I'm, okay, sorry. No. That's perfect, actually. This is the last bit. So we're already, I would say, starting to be able to answer the second question here with tidal disruption events. We can use their light curves to get constraints on the black hole masses and the luminosity with these very simple scaling relations. And so right now, we have about 100 of these events. But with Rubin, which is the Vera-Rubin Observatory, also called LSST, we're actually expecting to get thousands per year. And so our hope is that we can basically use these relations that we've now been studying with this subset of 100 events to get large populations of black hole masses with Vera-Rubin Observatory. And there's a lot more. I kind of talked about the most classic TDE case here. We're just discovering all sorts of weird, unique cases more recently as we expand our search. And so hopefully with some of those also they'll help us learn more about that first question about accretion physics. But for now, I'll just leave here and take questions. Sorry for going a bit long.